Mirja, welcome. Thanks for being here today. And it's very timely too. So you'll be talking about a protocol and about work in the IETF that I think is soon to become an official internet standard. So you'll know better, but my personal feeling is it's done. It's very close to becoming a standard. And it's not just that it's timely, it's also very important because the new version of HTTP is based on it. So without further ado, Mirja, thanks again for being here, and you have the microphone.
Thanks a lot. Yeah, it's a pleasure to be here, and you're completely right. The protocol will be published very soon. It's done, like the last editorial notes go in, but all the protocol work is done, at least for the first version. But I give you some more details in my talk. First, I think I should introduce myself. So I'm working at Ericsson Research since 2 years now. Before that, I was a postdoc researcher at ETH Zurich, where I also worked on an EU project looking at transport protocols, also internet measurements, understanding how the internet works and where the problems are. Before that, I got my PhD at the University of Stuttgart, and I got my diploma in Erlangen. Then the other part I'm working on is standardization. I'm very active there. I started standardization in the IETF, the Internet Engineering Task Force, where QUIC is standardized, when I was a PhD student. So basically right in my first year as PhD student. Since then, I've been sharing some groups. I also was an area director for the transport area for 4 years. So that's like the IETF is distributed into areas, and like there has to be somebody responsible for each area. And since last year, I'm the chair of the Internet Architecture Board. Sounds really important. It's not that much, I guess, but somebody has to take the position and somebody has to care about that. Okay, should we start talking about QUIC?
We should, but maybe I don't know how well our listeners understand the IETF. So how many areas are there? So, and how many working groups roughly? Just roughly.
Yeah, so there's 6 technical areas and the general area which cares about administration. The technical areas are transport, security, internet area, routing area, operations and management, and application area. And we have roughly about 100 working groups, I think. Some areas have more, some have less, and it changed, of course, over time, all the time, because new work is starting, old one is finishing.
And I guess it's fair to say if something matters on the internet, it has to go through the IETF.
So the IETF, I mean, there are multiple standardization organizations, but the IETF is the one that like does everything which is in scope for like internet-wide communications. And so QUIC is like the most nicest product, I would say, and I've been active in it, so I'm very proud of it. But like people know other protocols as well. So the IP protocol, which is kind of one of the base protocols, is an IETF protocol. There's HTTP, there's TCP. There are routing protocols like BGP, and so all these protocols are developed in the IETF and maintained in the IETF.
Right. Then let's have a look at QUIC.
Yeah. So on the next slide, I give you just a little bit of like what QUIC is a little bit of a brief history here. So QUIC is a new transport protocol, which is kind of an alternative to TCP. So hopefully you have heard of TCP, and I don't have to explain that part. QUIC has been developed as in kind of with an optimization, with in mind having optimizations for one specific use case, which is web traffic, so HTTP traffic. One of the biggest changes compared to TCP is that QUIC has basically encryption and TLS integrated into the transport layer instead of having it as a separate protocol, as a separate layer on top. And it takes multiplexing from HTTP into the transport layer, where I think it belongs, because, you know, that's just like how to independently send different things over the same connection. Standardization of QUIC started roughly 4 years ago in November 2016. And we are now about to publish RFCs. We have got a really nice RFC number, which is 9000, 9001, and 9002 for the base protocol, the TLS extension, or the TLS part of it, and the recovery part of it. But there are new extensions that we're working on in the working group already, and there might also be a version 2 at some point. Originally, QUIC was developed by Google, and they are also using it in production since 2014, basically. So they developed the protocol together with Speedy, which then became HTTP2, with the idea to like optimize the whole protocol stack from like the transport layer up to the application layer and try to get the most efficient and more secure. They started deploying it only for their own clients and their own servers. So when you had like a Chrome browser and you talked to a Google service, you would use QUIC eventually 2014 already. But then at some point it got mature enough that they brought it to the IETF in order to also have other companies participating, other browsers implementing it and other servers using it.
Do you know what version of QUIC Google is currently using? Because if I remember correctly, I haven't looked at the document in a long time, but if I remember correctly, the QUIC document at the very top says, don't use this in production and before it becomes an RFC.
Yeah, I have some outdated data later that they changed those versions very quickly, but they are in the process of deploying QUIC version 1, the IETF standard. They already have a version which is like much closer, or which is actually a standard version, because a long time they would use their own version, which had a different encryption, was like widely different from the IETF version actually. And they are already ready to push the button to deploy version number 1. They just wait for the RFC. Okay, so like what's the difference between QUIC and TCP, which is kind of the alternative for it? We look at this protocol stack a little bit. So when you look at HTTP traffic, previously you had the TCP protocol, then on top you have the TLS protocol for security, and on top there was HTTP, and the most recent version was at that point HTTP2. And with QUIC, the protocol stack changes a little bit. You still have HTTP on top. It's now called HTTP3 because using QUIC actually also meant to change the protocol there. And the biggest change you can see here is that the purple box just like moved from the HTTP layer into the QUIC layer. I explain later what that means and why that's important. The other big change, as I said already, is also that the green box now moved within QUIC. So security is not something that you put on top anymore. It's really integrated and you cannot rip it apart. It's like, and you can use it for more than just the payload. You can also secure some of the transport information with it. And then the red box here, congestion control and recovery, it's kind of the same as in TCP, but what we also did is like taking all the lessons learned from TCP and putting them into the protocol right away instead of trying to handle this with extension, which maybe simplifies the protocol a little bit, but also might make it more flexible in future to optimize here more. And then one thing to say is also that TCP runs on top of UDP, which sometimes is confusing to people because UDP is seen as the transport protocol itself, and then you add another transport protocol on top. But like I would never call UDP a transport protocol. all that UDP gives you is like headers, ports in a header. And so the reason for using UDP was twofold. One is it's the only way to deploy something in the current internet because there are a lot of boxes which just need port numbers. And so that's the way to give them the port numbers. And the other advantage was here that you, by using UDP and using a UDP socket on your local machine, you can actually implement QUIC in user space. And that makes it also more flexible to deploy new changes quickly.
So looking at HTTP3, it looks like it's like HTTP2, but way simpler because the streams have moved down to QUIC.
I'm not the HTTP expert, I have to say, so I think it actually didn't get that much simpler, and there's a lot of complexity about other things that's not shown in this picture. But like it got a little bit simpler, definitely, yes. So in summary, I already said the main features of QUIC is adding multiplexing and having this encryption integrated. But then there are also other differences. For example, stream and connection level flow control works different and is kind of enhanced. There are latency reductions. So by integrating the encryption into the transport, you can also save some round trip times when you establish the connection because you can do everything at once. There are new features that are taken from TLS, which is, for example, so-called zero RTT session resumption, meaning that you can send data right away instead of waiting for a while until the handset is settled if you resume the session, if you have talked to the server again. And there's a completely new feature, which is called connection migration, which is basically needed because QUIC is over UDP and there might be more frequent net rebindings, but it's also quite powerful feature because you can keep the connection alive even so you change the IP address. So that's also for mobility use cases, really, really nice feature, which TCP unfortunately doesn't support. So what I will do in this talk is to go into QUIC a little bit deeper, talk about the different features and how it works, what the advantages are. In the first part. In the second part, I give you some more insights about what the deployment status is and what we're doing in standardization and what comes next. Ready?
Well, I am.
Okay, let's start with the multiplexing part. So this slide gives you a little bit of history about where we came from and why this is important, and what head of line blocking basically means, because that's the part that we try to avoid with this change. So in HTTP 1.0, basically the idea or the scheme was that you could send one request and you got one response, and then after you got the response, you can send the next request. And of course, if like the first request takes a very long time, or the second request is suddenly more important than the first one, you just have to wait and you sit there, and that's called head of line blocking. You have to wait for the first one first. This was already partially addressed in HTTP 1.1 with so-called pipelining, where instead of sending one request and waiting for a reply, you could send multiple requests and then you get the replies afterwards. But you still had to get the request in the same order than you sent the replies. No, get the replies in the same order than you send the requests. With HTTP 2, this was further improved by so-called interleave requests. So now you could get them in a different order. And the second thing is also that there was already stream multiplexing, which means basically one request could overtake another request. So even if you start sending, in this picture, the big orange request first, you can later basically decide, oh, the green one is more important and I have to send it quicker, and then the green one might finish before the orange one. And that's realized by like just taking the data into smaller chunks, and you can interleave those chunks. So that was a big improvement and would like resolve the head of line blocking problem on the application layer. But actually there's still head of line blocking on the lower layer, on the transport layer. Because with this change towards HTTP 2, there was also a change. Instead of using multiple TCP connections for potentially multiple requests, as it was done previously to migrate this problem, now everything would be sent over one TCP request again, because that's actually advantage for congestion control and other optimizations. It's better to only have like to the same server only one connection. But then on the TCP layer, you still need to send and receive everything in order. So if you're missing a packet from one stream, even so you have received all the packets belonging to another stream, you still have to wait for that packet, because you have to deliver in order to the application, because the transport layer just doesn't know that there are different streams. And by putting this information into the transport layer, you now can actually avoid the head of line blocking there as well. So that's the idea here. Okay, next, let's look a little bit deeper into how a QUIC packet actually looks like. So here we see basically every QUIC packet has a header as shown in blue, and that's information that is needed to keep the connection working, and that's also partially visible to the path. And then each header has a number of different QUIC frames. In this picture, like in this first example, we just see like payload data for two different streams, which each is like in a separate frame. If this is now sent, or like in the next packet, we actually don't need to send the same streams. We can, like in this first packet, we see stream number 1 and 2, and then in the second packet, we decide we decide to send new data from stream number 1 and 3. Then in the next part, we see that we receive an acknowledgement from the other side. And this acknowledgement also contains some stream data, some payload data that is sent from the other side, but it also contains another frame, a control frame, which has the acknowledgement information. So if you remember about TCP, in TCP, acknowledgement information are in the header and visible to the path. And here in QUIC, acknowledgement information are part of the kind of payload after the header sent in the stream, because this information is only used end to end. And then the other thing you can see in this picture is also that, like, when you retransmit data, you don't have to retransmit the full packet. You can, every time you retransmit something, you can just decide, which payload is maybe more important. And in this picture, we retransmit the first chunk of stream number 1, but we don't retransmit the first stream of stream number 2 because we decided that the purple stream number 3 is more important. So we just send this. And this is also something that's not visible to the past, because every time you send a packet, it actually gets a new packet number, and that avoids some kind of or that provides more clarity than sometimes in TCP, where sometimes it's not clear if you retransmit packets, which packet has been received one, and so on. So that helps to keep the transfer more efficient. And then what you also see here is that basically everything which is sent in stream is completely encrypted, not visible to the path. Only the header is visible, and even the header, some information are encrypted using the same encryption context. So before we look closer into the QUIC header, we have one quick look at about like how this acknowledgement frame works. As I said already, the acknowledgement is not part of the header, it's a separate frame, which also means it's kind of more powerful to provide more information. So this is a lesson learned from TCP, that we now also provide, for example, some timing information when packets have been received, because that's very useful for congestion control and for configuring or like managing our connection. And the other thing that we took from TCP and put it right into the base protocol is that we now exactly provide information which packets have been lost, instead of just saying what part have been received and then leaving some ambiguity here. So that all is more powerful, and is also something that can be used for future congestion control, for more experimentation and for optimizations in that space.
So you're basically saying that that information is not being used right now.
Part of it, so there are two things that you can use this information for. One is retransmission, of course, like understanding when and which information to retransmit, and that's already used TCP with the sort SEC extension. And the other part is using this information, and there's also timestamp extension in TCP, which provides some of this information as well. And then the other part is using this information in congestion control, and there not all of the information is used yet. But some are, because congestion control is also a moving target, and new things develop all the time.
So if I remember correctly, when QUIC started out, they decided they wanted to go with GNU Reno for congestion control. Is that still true, or has that changed?
So it's not like they wanted to go with GNU Reno. They said the standard should point as a standardized congestion control. So the standard is supposed to give you at least one congestion control scheme that is like known to work on the current internet, and that's actually not Reno, it's QUIC now, because QUIC has been documenting standards in the meantime, so that we rely on. But it's also not meant that everybody needs to use QUIC. It's actually meant to be flexible and to provide some space for exploitation.
All right.
Okay, now let's actually look at the packet header a little bit more, how it looks like and what information is provided. So with QUIC, there are two different packet headers. One is called the long header and the other one is called the short header. And long header is used during the handshake, where like the connection is set up, information is distributed to both sides, and state is set up. And so you need a little bit more information. And then the short header is used later on for all other transmissions. So you can just save some bits, because bits per packet are actually important for efficiency. What you can see here is that for the long header, you have the so-called connection ID, both for the source and destination, and then usually in the later part, you only have, optionally actually have the connection ID for the destination. And this connection ID, I explained later a little bit more, that's what's needed for this new migration feature, where the IP number can change, but you still have the connection ID, so you can still identify if you get a packet to which connection it belongs. Short header has a few bits here, and the one that I want to point out here is a spin bit, also something I will talk about later a little bit. So this is like one single bit that has actually been added to the header to be visible on the path and to be used on the path to get round trip time information for troubleshooting and monitoring. which is also which is in a sense a new feature that it's like an explicit service, but it's also a replacement for something that was done previously with TCP information and now got away because this information about acknowledgement, timing, and so on is not visible anymore. So, but before we talk about these features, let's look into the handshake a little bit more so you understand what the difference is. And this is mainly talking about how latency is optimized with QUIC during the handshake. So if you look at TCP with TLS 1.2, you can see that usually you have 3 round trip times before you can send any data. This is because first you have the TCP handshake, and then TLS needs another 2 handshakes before this crypto context is up, and that's the point of time where you can start sending data. With TLS 1.3, there was already an optimization that you could send data earlier. So it was reduced from 2 round trip times to 1 round trip time. And now because you combine both of this blue and the green handshakes here, basically, you're down to 1 round trip time. Or like on the next slide, if you have talked to the servers previously and you know that the server probably already still has some information about your crypto context, you can actually start sending data earlier. So that's a feature of TLS, which was already there in TLS 1.3, as you can see, but it was TCP and TLS 1.3, you still had to wait until the TCP handshake is finished. And with QUIC, you can basically start the handshake and sending data at the same point of time. So this is especially for like services where you need a quick reaction and you have talked to before, very important and makes a user difference.
I assume that's a huge amount of connections on the internet. I mean, if you go to Google, back to Facebook, back to all these services that you use very frequently, there's a huge amount of connections that will benefit from this.
Yeah, it's definitely huge amount of connections to like the big providers, right? Because they also offer different services, so you can make use of that. Okay, now let's talk about a quick connection migration a little bit. So the original idea why this was used is because today you have these kind of NATs, so network address translators in the network, mainly in IPv4 networks because running out of IPv4 addresses. So the solution that people came up to this is that instead of giving every user, every client that is connected to a network an own visible or like widely visible IP address, you use like the same IP address outside facing and translate it at a box at some border. So that itself is fine, it works well. The only problem is if you now start sending a lot of data over UDP, what you see is that these IP addresses actually change more frequently than you're working for, because the way these boxes are usually implemented is that they have very long time at TCP traffic, because TCP traffic has a very well-defined start and end. You can see the handshake, you can see the FIN bit and so on, so they can maintain state very well. But for UDP, you don't have like this handshake in generally. So what they do is they have like very short timers where they just remove state if the connection is not used for a while. And these timers are so short in the range of like only 30 seconds sometimes that you might just pause in your connection and then keep sending again and suddenly you have a new IP address. That does happen with UDP quite often. So this was actually a problem that QUIC has to address because it runs on top of UDP. And the way it was addressed was by adding this connection identifier field to the header, so the server or the receiver of the packets can still understand which connection the packet belongs to, even if the IP address changes. As I said, this feature has actually been quite powerful because that can also be used if you really change network and you get a new IP address. And that's a scenario that you have very often when you, for example, switch your connection from, like you leave your home and you switch from Wi-Fi into your mobile connection, because these are completely different networks. So you get a different IP address. And in this case, with TCP, you had to restart your connection. But with QUIC, you can actually survive and just keep sending your data.
Are there also, for the NUT problem, does QUIC send keep alive messages to keep the NUT binding alive?
So QUIC can send keep alive messages. They are called ping frames, but it's a trade-off, right? So it's additional overhead and you don't know exactly which time frame you should send them. And so effectively, it's recommended to rather not the ping frames and rather kind of either hope you survive using the connection ID, or QUIC is also very quick in restarting, right? Because you send data right away. So if you actually figure out your connection is broken, you can just like restart and send data right away again.
All right.
Okay, and then the last feature I want to talk about a little bit is the QUIC Spin Bit. So I have to say I was involved heavily in the discussions here and in getting this out, and everything we got out was one little bit. It's a very powerful bit. And the important part here, and the important part why there was so much discussion, was that, you know, on the one hand, we try to encrypt as much as possible because all kind of data can be sensitive, or also you don't want to avoid that somebody's kind of dealing with your data, interfering with the process and maybe breaking something. And now the spin bit is actually a piece of information that has been added afterwards again to provide explicit information to the pass, acknowledging that some of this information is really important for the network to know, to keep the network viable, to manage the network, to have troubleshooting, and to monitor what's happening on the network. So as I said, the spin bit is only one bit in the header, but what the spin bit provides you is that you can get a rough idea about what the round trip time is between the client and the sender. And that in itself is not the most important information, but for monitoring purposes, for example, it's important to see how this round trip time changes over time. So if you have a sudden increase of all your traffic of round trip time, this might be an indication that there's a problem somewhere in your network, for example. So this is just like an indication about like how your network maybe is, or if there are any problems. How does it work with one bit? So one bit is actually quite a lot because we have one big bit on every packet. And that's what we use here. The mechanism is very simple. The server kind of spins the bit, that's why it's called spin bit, and the client just reflects the bit. So when you start sending a packet, the server just selects, like with the first packet, the server just selects the 0 or 1 in the bit, and then the client receives this packet and remembers this value, reflects the same value with the next packet that goes back to the server. And then from there on, whenever the server receives a packet, the server will spin the bit. So instead of sending the same bit on the next packet that it sends out, it actually sends the other 1 or 0. And with that, and there's actually a little animation here, so you can look at that. But with that, what you get as a passive observer in the network is that you get like a whole bunch of packets with either zeros, and then afterwards a whole bunch of packets with ones. And if you measure the time between every time when the bit changes, you actually see the round trip time it takes from the server to the client and back between those two entities. And that's actually, this is actually a good example of why I'm doing what I'm doing, because like when I was a student, I was really fascinated when I'm looking at TCP or other protocols by these little tiny tweaks, which might be so powerful. And so when I went actually in standardization and figuring out how these protocols were developed, and it was really nice to actually talk to the people who developed these protocols, they are still around. But then figuring out, how much discussion there is and like how this all happens, it was really interesting for me. And so I'm also proud to be part of this like one bit here in the QUIC protocol.
And if I remember correctly, this bit was very controversial from the start, yes, because people feared that you can glean something from that information that is bad for the privacy of the user, but nothing was found really, I think.
Yes, so I think what I said earlier, it was this general notion of should we actually provide a mechanism that is explicitly providing information to the network, or should we hide as much information as possible? So it was very, not so much technical, but more idealistic or general principles discussion. That's why it took so long. It took more than a year to get this one bit in, but there was like also a lot of evaluation about, how this works, does it break? And that's also what's shown here, that we, for example, showed that like even if reordering is happening, you can have easy, simple heuristics to figure out that there was reordering and it still kind of works, it's still kind of stable. But in the end, it was an interesting process.
But do you know if every client will actually support the spin bit?
So generally the spin bit is optional. So both the client and the server have to actively activate it to make it happen. And usually all the implementations that do implement the spin bit have some kind of a button to activate it or not. Unfortunately, not all implementations even implement the spin bit. But we see some interest by some of the larger providers, because usually those providers aren't only the one providing the client and server implementation, but they also have their own networks to operate, so they do see value in it. But this is one of the questions that are still important to answer when we deploy QUIC on a more wide scale in the next couple of years.
That will be interesting. Do you know, if you said deploy more widespread, I think it's already a significant portion of the internet's traffic, isn't it?
Yes, so that is actually what I'm talking about next. So we talk now about deployment and standardization, and then on my next slide, I have some numbers. Unfortunately, these are slightly outdated. They are much higher now already, but I hadn't a chance to get some newer numbers. But I think it still gives you some impression. So these numbers are from 2019, where I actually went ahead and asked all these different companies, like, what's the current status? And it was already more than 50% of YouTube traffic that was already using QUIC, and it's probably higher now. At that time, it was still the Google version of QUIC, so hopefully that will also change next. For Facebook, it was kind of basically all of the traffic for certain applications. But even then, this is the content provider side, right? So they can decide, they can only look at their own traffic, and they can decide how they want to use QUIC for their own traffic. Even if you look at the network provider side, and mainly at the fixed broadband in this case, there was already 10% of the downlink traffic, which was QUIC 2 years ago. So that's probably also larger. For Akamai, which is one of the big CDNs, it was slightly lower, but they also have a deployment strategy where they try to step by step increase the amount of QUIC traffic to make sure all the network is set up accordingly so it can handle the QUIC traffic. And then we also got a number from more recent number from AT&T, where they already had like around 25% of video traffic being QUIC, for example. Most of that probably YouTube, but maybe other operators as well.
I recently had to check the numbers from the COVID-19 crisis, so March, April 2020, when network traffic significantly changed, obviously. And I remember that YouTube globally was the most contributor to traffic, and it was probably, I can't remember the exact figure, it was probably like 16, 70%. And if half of that is QUIC, then that is significant.
Definitely. I mean, it depends on how you look at traffic. There are two different metrics which are mostly used. One is like the amount of data, and the other one is the number of connections. And for the amount of data, video traffic is, of course, like one of the big contributors, right? If you look at the number of connections, it really depends on which company has rolled out QUIC for which use cases and so on. So, yeah.
I think AT&T was one of the few companies that actually, so most of the companies said how many percent more traffic they have during COVID-19, but AT&T was one of the few companies that actually said how much traffic they have per day in their global network. And I think that was 950 petabytes per day. And if a large fraction of that is video, and a large fraction of that is QUIC. So that's actually quite interesting to have these numbers, thanks to COVID-19.
Yeah, I mean, what it means is that QUIC is real, right? It's not on the paper only. It is actually deployed in more to become, definitely. So especially if you look at web traffic, my expectation is, because QUIC has been optimized for web traffic, my expectation is that it will be used by all the big providers. And so, like, you know, a large part of web traffic will be QUIC in future.
Do you think other types of traffic will move on to QUIC? Because it doesn't look like a general purpose transport protocol. It looks like something that is HTTP only mostly. Yeah,
so I have more information later. Right. But no, but like more generally, so QUIC is designed as a general purpose transport, but like, you know, HTTP was the main and only use case that we looked at for now. So, you know, if there are cases where we figure out we have to optimize for different use case differently, then probably that will go into version 2 of QUIC. And there are already people who look, for example, at using QUIC for DNS traffic, using QUIC for WebRTC traffic, and so on. So all these things are ongoing. I don't expect that all traffic will move to QUIC, and we never will see TCP again in future. Especially there are some corner cases where you might not need encryption. And maybe in this case, TCP is still preferred. But also because yeah, it's like you can, the idea is to have different transports, always use the right transport that fits to your application. On the other hand, there is like a huge hype around QUIC at the moment. So a lot of the people look at QUIC no matter what, no matter if it's benefit or not, just because it's a more modern protocol. And of course, there's also, when you make a decision for a protocol, there's a question about maintenance. If you have a system where you use different transport protocols, you have to maintain all of them, right? So maybe there's a question about which one you want to maintain in future.
And I, for one, think DNS has enough transport mechanisms at this point in time, but that's just me.
Yes, but given that DNS is already available over HTTP, just sneaking QUIC underneath is not a problem, actually, right?
Yeah, that's a good point.
Okay, so this one is again a very outdated graph, but I wanted to bring this in because you had like an earlier question about this, and this is just showing how Google was rolling out QUIC in the early times. And what you can see here in the left graph, for example, is that there was a period in where they like ramped up QUIC slowly, and then they even shut it down for a while because they detected a problem, turned it on again, and then there was like a big increase where they decided to deploy it differently. So this just like shows one of the deployment strategies, but different companies might have different strategies. And then like to your earlier question, on the right side, you see like how Google was changing versions, because they were changing versions very often when they would always change version then when they roll out new feature or have some changes and so on. That is actually an idea of QUIC, that you can be more flexible about rolling out new versions. So far, we have only standardized one version, and there are different extension mechanisms as well. I talk about this later. But the idea is to be more flexible here than we used to be with TCP. We're kind of, all the basics were very static.
This is an amazing graph because you see how quickly a new version is actually replacing an old version completely. And if you look at TCP, if you had a compare like a TCP option only, right, this would probably be tens of years that you see here until you reach 100% penetration on the internet.
Yeah, it will definitely not look like this in future anymore, because that was Google only, and that was only like part of their traffic, right? So that was the clients that were already kind of very flexible to be updated frequently and so on. So now that we deployed more wide scale, we probably have to accept that some of the older versions will stay out there for longer, and we have to manage them.
Yeah, that's true.
This picture or this slide is just like a little bit more about like what's going on, how the IETF works, and what's happening behind the scenes. So this is the Interop metrics that the QUIC working group is using to test their implementations. And what you can see here is that there's like, I didn't count them, like 10 to 15 or maybe 20 different implementations of QUIC. Not all of them are kind of product ready implementations. Some of them are maybe more toy implementations or test implementations. But some of them are actually, if you could read what's written here, are actually from the bigger operators. So there's a stack from Apple, there's a stack from Microsoft, there's a stack from Google, there's a stack from Mozilla, and so on. And these implementations also will go into in live and will be used on the internet. So a lot of work there, and also very code and implementation driven was the development in the working group of the QUIC protocol.
Do you know there's F5? For example, in there, and it looks they only supply the server part. So there's no, or do they don't they? Is there a significant difference in having a client and a server? Because F5, if I look at the graph on the client side, there's blank, there's nothing. Or is this?
So I didn't look into their implementation. I'm not even sure if it's open source. Not all of them are open source.
I see.
It might be that they only for the testing provided a server and they didn't test like an own client instance. And there is a difference because QUIC has a model of client and server. They have different roles. So sometimes if you would decide to only implement a server, you can avoid, for example, you never have to open a connection, whatever. So you could probably, reduce your code. I don't know. I didn't look into that part. F5 is also a company that, for example, builds load balancer, was very active in the process with a discussion about how to use the connection ID also for load balancing within your cloud network, basically, for example. So they are not providing endpoint implementations. I guess they're looking into this implementation for their own purposes of doing network load balancing and other kind of things.
Right, it's very interesting. And the greener, the better, I assume. So the greener, the more interoperable.
So there was also a whole process of defining, which feature we want to test at which point of time. And so there were different things you could test, a different set of tests, and the greener, the more of the test you have been passing. So over the time, and actually, I don't know when I took the screenshot, so this looks probably different now, but over the time, the implementations would implement more and more and more features. And so you could also interop on more and more features.
That's good to see that there's a lot of implementations. It just reflects the interest in the protocol.
Yeah, and it was a very high energy process in the working group. A lot of people, a lot of implementation, a lot of discussions as well, of course. Also a lot of work, because it was not only the QUIC protocol that we've been working on, but also HTTP or changes to HTTP, which were actually quite big. So different communities had to talk to each other. Very active process, a very good experience, and I think a very nice outcome. Yeah, so I think I have two more slides, one talking about extendability, and then the next one talking about what we actually have three more slides, okay. One talking about extendability, and then talking about what's happening in terms of extensions in the IETF right now. And here I want to put a quick note that actually encryption also helps with extendability and deployability, because what we have seen with TCP in the past is that it was really hard to add new, for example, TCP options and so on, because there are boxes in the network which didn't expect to see a new option, and then they would just break or would throw away the option or do something unexpected effectively. So with TCP, it was still possible to extend the protocol, but you always had to cope with those cases where it wasn't possible. You always had to implement extra code. You always have to make sure things doesn't break entirely. That made the process like more complex than it was originally intended. Having all this information encrypted and not accessible by the pass means also that nobody on the pass can interfere, nobody can break it. So that hopefully reduces what's called ossification, where we reach a point where you cannot change the protocol anymore, but hopefully we will be more flexible to change the QUIC protocol. And it's also that the QUIC protocol basically is designed to have only a very minimal set of things that have to stay constant over version. And this is called invariance. And we made very clear to define what these invariants are and make sure that everything else can change. So basically, if you have these invariants, and some of these things are what's in the header, some of the bits in the header, not sure if the connection ID is there, but it might be, I have to look it up. But if you keep that stable, you can change everything else and you can make it a completely different protocol. You can throw away all frames. You can decide to not use multiplexing anymore. You can have a completely different encryption, whatever. You can just pretend to be QUIC on the outside, but a different protocol on the inside. And so the idea here was to, be able to innovate, to evolve over time, but also to keep the rate of innovation and changes maybe higher than it was with TCP.
It will be interesting to see if that turns out to be true, if there's a lot of innovation in QUIC.
Yeah, so my guess is that actually this idea about changing version numbers very often, as Google did in the earlier times, that will not happen. We've put so much time into version 1, so it's probably there to stay for a while. But there are other extension mechanisms as well. The other extension mechanism, for example, is just adding new frames, adding, negotiating new kind of behaviors during the handshake and so on. And that's where we're already very active, and it's also on this next slide, where we already have an extension to also support datagrams, for example, in QUIC. So while TCP was streaming only, and that means all the information has to be delivered in order and reliably, QUIC actually also provide a mode where you can just send data out of order unreliably. And this is in the same transport protocol at the same time. So it's like covering a whole lot more use cases than TCP was previously covering. So effectively, this covers use cases where previously you would use UDP and then kind of develop your own minimal transport on top, and now you can maybe use QUIC.
Would it cover VPNs too?
Yes, that's on the next slide. Okay. I'm not sure if that's if I would phrase it like this, but we do work on VPN-like scenarios. I talk about this on the next slide for a second. Other things on this slide is, for example, there is a support document talking about how to realize load balancing. That's also something you mentioned earlier. There's already a document proposing improved egg control handling, providing even more information in the eggs that then can be used for congestion control, better, more modern congestion control. And one of the big topics at the moment is version negotiation, because with version number 1, we said we only have one version. We don't need version negotiation right now, but for the next one, we need it. So this is one of the big topics. Yeah. So like even more things here. There was like the idea to also add forward error correction. There is still a discussion about adding multipass, which is something that you already have with TCP, MPTCP. There's a multipass version of TCP, not there in QUIC yet. A lot of discussion about it. If the advantage of multipass is so much bigger than just having this pass migration, which is already there. There's discussion about adding loss indications to the QUIC header, for example. So these are all kind of ongoing discussions, no decision yet.
I find fact interesting. So that is it only for bit errors, I would assume, right? So if there's a bit error in the packet, you can correct it. But how often?
So no, so this is this is kind of in the whole discussion about providing some kind of partial reliability, right? And covering a broader set of use cases. So we already have now this, and this is something that actually wasn't discussed lately in the working group, but it was part of the initial charter. And we already have now this datagram support where you can transmit unreliable and in order, and like usually in those cases you would add some further error correction on the application layer. So the question is if you could move that into the transport as well and further optimize.
Okay, I see. Mm-hmm.
And then this is actually my last slide. Now, and this is also the one where I mentioned mask, which is the VPN effort we have in the IETF. So it's not only work in the QUIC working group where we provide extensions, but we now also see in the IETF a lot new working groups which use the QUIC transport protocol and put something on top. And one of them is, for example, the web transport working group, which is providing an interface that is used by W3C to do all kind of web transports over QUIC. And the other one that we already have is a mask working group, which is a protocol to use to extend HTTP Connect actually. But effectively what you get from it is like a more general kind of proxy protocol where you can set up a QUIC tunnel to a proxy and then forward traffic within the tunnel to a target server. And then there are other things which are under discussion. So I mentioned also DNS over QUIC, which is not an own new working group, but it's an adopted working group document in an existing working group. So yeah, exciting times, more to come. We will see more deployment of QUIC, we'll see more work on QUIC, and we will see more usage of QUIC, I think.
Definitely. Well, thank you very much. This was very educational.
Was a pleasure.